Hello guys, so today I'm going to be explaining the solution for this problem, hidden colored graph, which is the July Cook-Off problem. So I think I'm in the division 1 version, but it was in other divisions also. A second. I think it was in division 3 also. It was there. This is July Cook-Off, right? Yeah, I think in division 3 also this was like the last problem. Yeah. So, okay. So last problem of division 3 and somewhere in division 2 and in division 1 also. So let's discuss this problem. So in this problem, I think this problem was authored by Monogon. Yeah. So this was by Monogon, and so this is like the hidden colored graph problem, in which you are given a hidden undirected graph with n vertices. So there's like a graph of n vertices, but we don't know it, so it is hidden. And we know that there are no self loops or multiple edges, so it's like a simple graph. And each vertex is colored either black or white. So this will be helpful later, but the colors are also hidden from you. So we don't know what are the colors of the graph, but each vertex is either black or it is white. So to make a query, we first choose the vertex V, and the interactor will respond with the current color of V, and then it will flip the colors of all the vertices adjacent to it. And a vertex is not considered adjacent to itself. So I think this is quite clear already because like there are no self loops, right? So if you are adjacent to yourself, it would mean that um, you have a self loop, but that's not what's happening. So the color of B does not change. So like if you even if you like keep on asking the queries on the same point, the color of that point won't change. And we have to use at most 6,000 queries, and we want to find the adjacency matrix of the entire graph. That means we need to find all of the edges that are present in the graph. So the interactor is not adaptive. That means the graph and the colors are fixed in the beginning. So yeah, it's not like depending upon your queries, they will um, try to adopt the interactor in such a way that if it is possible to make your answer wrong, it will change the input in a way that your answer is wrong. So that's not something that it will do. Usually, this line means that like if it is not adaptive, it means that even a randomized solution can work, like depending upon whether it is possible or not. If like a randomized solution is possible, then even that can work. But if like the checker is, if like the interactor is adaptive, then usually random solutions also don't work because like what happens is um, like even if you are trying to randomly find something, the interactor will be adaptive, and it will like you kind of have to trap it to give you the right answer, and then you have to tell that okay, this is the right answer. So that's not what's happening here, so we don't have to care about it. In simple words, it is something like the hidden graph, and the colors are all fixed in the beginning, and the interactor is just answering based on what is currently present there. So yeah, so we don't have to worry about that interactor cheating upon us, but that won't happen with our solution. Like the solution that we have, even if the interactor was adaptive, our solution would still work because we don't have like a randomized solution or anything. Okay, so let's see what the interaction is like. So we initially get a integer n, and that is the number of vertices in the graph. And to ask a query, we can output question mark space v, where v is the vertex that on which we want to perform the query. And the answer that we will get will be either b or w, that is the color of that vertex. And all the after making this query, all the adjacent will get flipped. So to print the answer, we can just output the exclamation mark, and then all the on the next n lines, we have to print the length, print n strings of length n with symbols 0 and 1, which denotes that whether there is a edge between these two or not. So yeah, so that's the whole idea behind the problem. For example, here you can see that first you get the number of vertices to be n, and then question mark 1, that means we ask the color of 1, then we ask the color of 3, and color of 2 and 3, and so on. And like they keep on changing the color of the all the adjacent vertices also, and you keep on getting these values. And when you're finally confident that you have the correct answer, you can just print the exclamation mark, and you can print the entire matrix. So yeah, now that's what it is. And for the interaction, like you have to make sure that you flush the output before printing each line. So this is like something that is common in interactive problems, that you cannot just keep on printing and taking input without flushing the output, because if you haven't flushed the output, the interactor won't know that you have printed something, and then it won't be able to give its response. So you have to make sure that you flush the answers. So for that, we usually use this symbol called, like we usually do in C++, you can do cout.flush or something like cout endl. So when you endl, then it automatically flushes it. But yeah, anyway. So let's see what the problem is like and how to solve it. Okay. So what you essentially have is like a graph, and this graph is hidden from you. So you don't know what this graph is, but yeah, this graph is there. It is a fixed graph, and all the vertices have some color. So for example, some can be green, and the others can be like red. Actually, it is black and white, but here I'm explaining with red and green. Yeah. So like this, they are colored as well. And what we can do is we can kind of ask queries. For example, let's say if we ask a query on this vertex, so you will get this color, but both of these things will get flipped. So for example, like if it was initially red, it will become green. And if it was initially green, it will become red. Yeah, something like this will happen if you ask a query on a vertex. So yeah, so this is a little, so this makes the problem a little tough because even if like you try to like to find an edge, you would try to do something like you first take the color of the vertex and then you see the others are changed or not. But that is a little problematic because what will happen is um, when you like ask the color of the second, the third will change, right? So it is something like let's say you have the vertices from 1 till n, right? And so what you will do is first you will see the color of one. So let's say the color of one is black. And next what you want to do is you will like when you see the color of one, all the vertices which are adjacent to one, their color will change. So now you might want to scan all the vertices and see whose colors have been changed. So even if you initially had the colors of everything, so there will be one problem that when you ask the color of this vertex 2, uh, maybe you will understand whether it is changed or not. But after that, the rest of the area becomes unreliable because like even the things that are adjacent to 2, they are also flipped. So some things are flipped because of 2, some are flipped because of 1, and some are flipped because of both, so they are not flipped at all. So we cannot say with certainty what is going on in the rest of the area. So, yeah, so that is one problem that will be there. So yeah, and if we talk about the constraints, we have at most 6,000 queries. Let's see how will that work out. And we have n vertices. So regarding n vertices, with n vertices, the total number of edges, the maximum number of edges can be nc2, which is n into n minus 1 by 2. So in this case, if we put n equals 100, this would be something like 100 into 99 by 2, or I think 4, 5, 4, 5, something like that. I think, wait a second, 5, 0, 4, 9, 4, 9, 4, 9, something like this, 4, 9, 4, 4, 9, 5, 0 or something. Let's just do this. 50 times 99, right? Yeah, 4950, exactly. So this will be like 4950, which is smaller than 6,000. So it will be fine if you can get each edge in like one query or slightly more than one query, but that like that's not easy. Not something that we can easily do. Like even if we try to find everything, like if we want to find whether there's an edge between x and y, the only thing you can do is like first see the color of x. So let's say if this is black, and then you will see the color of y, and let's say it is white, and then you will see the color of x again. So the color of when you see the color of x again, if it is still black, that means there is no edge between x and y. But if it has been changed, then there was an edge between x and y, and in this way you can find an edge in three queries. So in three queries, you can find a single edge. So to find a single edge, you have to use up three queries, and If we use 3 queries for each edge, then that is bad, and yeah, so that won't work. So what we can do is we can kind of decrease this 3 to a 2, and for that what we can do is first we can find all the edges from x till something else, right? So what we will do is, for example, let's say x equals 1. So we want to find the edges between 1 and everything else. So what we do is, first of all, we find the color of 1, let's say it is black, and then we find the color of 2. So we don't care whatever the color is, but then we will try to find the color of 1 again. So what will happen is, this color will either be black or white. So if it is black, that means there is no edge between 1 and 2, and if it is white, that means there is an edge. But once we finish this, we still have the color of 1. So since we still have the color of 1, we can just use 2 queries to get the edge between 1 and 3, whether it is present or not, and we will still be knowing the color of 1. So next step, we can find whether there is an edge between 1 and 4 or not, and in this way, on an average, we can find a single edge in just 2 queries. So in 2 queries, we are able to find a single edge. So, but again, if we try to do this, this would be something like around 10,000, like a little less than 10,000, but still. So this is definitely greater than 6,000, and yeah, we cannot do this either. So on an average, we want to spend not more than one or 1.1 queries per edge. So to do this, we have to realize, we have to see how we actually improved from 3 to 2. So to improve from 3 to 2, we noticed that we improved from 3 to 2 when we were able to maintain the color of 1, when we were able to, keep it in our knowledge what the color of 1 would be even after our queries. So in this way, we were able to reuse that information, and in that sense, we were able to decrease 1 query per edge. So to do it again, we need to have even more information about the colors, right? So to do this, let me describe this method in like an inductive way. So let's say you have let's say you only consider the graph from index 1 to x, right? So we only have the graph from index 1 to x, and you have all the information about the graph. For example, you have all the edges that are present between 1 to x, and you also know the color of every vertex from 1 to x, right? So that means you have the adjacency matrix of size x cross x, but like there are more elements, like because this is not x, this is n in total. So all these elements you don't have, but this x cross x thing you already have. So let's assume you already have this x cross x, and you also have the color for each of them, right? So let's assume that we have that. So as I said, this is like a inductive kind of method that we're talking about, and by inductive I mean like mathematical induction kind of thing, where we first make an assumption for a general x, and then we show that it works for at least the initial x, and then we prove it for x plus 1. So something like that we do. So let's try to do that here as well. If we talk about mathematical induction, it is something like a domino kind of thing, and we show that if this x thing will fall, then x plus 1 will also fall, and we just have to push down this first one, and then all of them will start falling, and we can do it for everything. So yeah, so that is something that we want to do here. So let's first show that it is possible for x equals 1. So how is it possible for x equals 1? Because there will be only a single vertex, and this adjacency matrix will be just 0, because we already know that there are no self loops. So we know that 1 and 1 have no edge. And how to know the color of 1? We can just run 1 query, and then we will be knowing whether the color of 1 is black or white. So yeah, so this thing can be done for the first element of the entire set. And now let's assume that it is already being done for x, because if we have done it for the first element, then obviously this assumption is valid. Now we want to have a way to grow this from x to x plus 1, right? So we want to be able to do it for the first x plus 1 elements. What this essentially means that we kind of need to have this extra layer in the matrix. This value we already know it is 0, and this is like a reflection of this itself. So we just have to find this thing, and this thing we will already get. So we kind of need to find an extra column or like an extra row inside this matrix, and then we're done. So how do we do that? So for example, we have the colors and the this thing. I mean, we already have the colors and the adjacency matrix of all the elements from 1 to x. So how do we find the color and the adjacency matrix of all the elements from x plus 1 to from 1 to x plus 1, and then we want all of these elements, and we also want the color, right? So getting the color is easy. Just do a query on this. So just by doing like a query here, just by querying x plus 1, we will be able to get this color, right? So color we will get, but what about these values? So to get these values, it's a little simpler now, because as I said, we knew the color for all of these values, right? So we already have the color for all the values from 1 till x. And once we query x plus 1, all the nodes that are adjacent to x plus 1, they will change. But all the values from x plus 2 till n, we don't care about them, right? So for now, we don't care about them. So we will just ignore them, and we will focus only on these values. So we already know the color of all of these, and after doing a query on x plus 1, we know that some of them have been changed, and whichever ones have been changed, we know for sure that they must be adjacent to x plus 1. So we need to check for the colors of all of these vertices, right? But again, won't that problem arise again, where I said earlier that once we check the color of 1, it might change the color of 2 or 3 or 4 or x, right? So how do we tackle that problem? So here that problem is already been tackled, because we already have the adjacency matrix for the elements from 1 to x, right? So this will work here, because we know that when we try to find the color of 1, a lot of these will change, right? So a lot of these will change. But since we already know this adjacency matrix, we know for sure that exactly which ones will change. And then we can go and manually change them in our own memory as well. So in that way, we can, like, for example, let's say if there's an edge between 1 and 3, and there's an edge between 1 and 4. And the color of 1 is like black, and this is black, this is white, this is white. Okay. What will happen is, when we query for x plus 1, let's say there is an edge between 1 and x plus 1, right? Or let's say there is no edge between 1 and x plus 1 for now. What will happen is, when we come back here and we check the color of 1, we will get the color black. So we know that there is no edge between 1 and x. So that is fine. But once we have queried 1, the color of 3 and 4 would change. So we can just change it in our own memory also, because like we know not only the colors but also the edges. So we know that since 3 and 4 are adjacent to 1, we will just go and change them to black, right? And after that, we will check the color of 2, then again do the same thing, and then we will check the color of 3. So color of 3, we think it should be black if there is no edge between 1 and x plus 3, between 3 and x plus 1. But if there is an edge between 3 and x plus 1, then this would be white, but we expected it to be black. So now we can tell that there was an edge between 3 and x plus 1. So in this way, we can find all the edges. Just make sure you take care of one more thing, that for example, if there was an edge between 1 and x plus 1, then what will happen is, once you query 1, obviously this we expected it to be black, but it was white. So we know that there is an edge between 1 and x plus 1, and then we will change the colors of these 3 and 4 also. So this white will become black, this white will also become black. But then we found the color of this x plus 1 in the previous move, right? Like we found black earlier. So since there is an edge between 1 and x plus 1, doing this query will change this element as well. So from we have to remove this black here and put a white here as well. So yeah, make sure you keep updating the color of the x plus 1th vertex also, because otherwise it will be problematic. So yeah, so in this way, let's try to find the total number of queries that we're doing. Okay, so to move from x to x plus 1, first of all, we are doing one query, and that one query is to find the color of this. And then after that, we are doing X more queries to find the color of everything else. So basically, we are just doing X plus 1 queries for the induction step. And for the initial step, we did 1 query. And after that, we will just do X plus 1 queries for each step. So it will be like 1 plus 3 plus 4 plus 5 plus 7 and so on. I think, just give me a minute. Yeah, actually, yeah, so it is like 1 plus 2 plus 3 plus 4 because we will consider X equal to 1, right? So after that, we will try to add 2. So it will be like 1 plus 2 plus 3 plus 4 and till n. So I think we can do it in exactly 4950 queries, right? So we can do it in 4950 queries every time, and this will always work. But let's also see the time complexity. So if we talk about the time complexity, after each query, we might have to change like n vertices that are adjacent to it. So we are doing like 4950 queries, or even we can call it like we are doing around n square queries, n square by 2 in fact. We're doing n square queries, and after each query, we might have to update like n elements inside our adjacency matrix, not in the adjacency matrix, but we might have to change the color of n more elements. So that will take like n operations to do it. So the total time complexity would be like n cube by 2 or something. In fact, n cube by 4 maybe, but it doesn't matter. We can just say it is O of n cube. So yeah, so the running time of the algorithm is like O of n cube, and we are able to do it in like 4950 queries, and the number of available queries is like 6,000. So I think that is well enough. We can even look at some code. Right. Let's see. Queries code. Pretty sure it is something like that only. He's storing the adjacency list, and then also like a certain column. So they tried to take input for the entire column. So like just doing the these are the queries. So doing all the queries together for 1 till n, and then from that information he is deducing everything, and in that way he's able to solve it. Yeah. Um, I think this was not exactly the same as the solution I was talking about. What I was talking about, okay, even this is different. So here we can see it is like a randomized solution, maybe. Mm, Again, it works because as I said, the interactor is not adaptive, so that also works. Let me just try to explain the pseudocode for my own solution, because I think my solution is like very clear. We'll see the editorial also. Editorial solution should be similar to mine only. Yeah. So if we talk about the pseudocode for my solution, it would be like, first of all, let's try to like we keep an array for the colors, and we also keep the adjacency matrix, right? So this is like a n cross n matrix. So these two things we will keep, and then we will run a loop from 1 till n. In fact, let's first find the color of 1. Let's say the color of 1 equals query 1, right? That is fine. And then after that, we can just loop from, let's say we loop from 2 till n. Let's say the variable I, with the looping variable I, we loop from 2 till n. And then what we will try to do is we will try to put this element 2 inside our known things. Okay. So to do this, first of all, again we will loop for j, and j goes from like 1 till I minus 1, in fact, right? So it goes from 1 till I minus 1, and in this range we will try to see the color of this. Okay, so something like, if there is no edge between hmm, first of all we query the vertex j, right? And in that way we will be able to get that color, and if that matches with the original color, then we can say that there is no edge. Otherwise, there is an edge. So in that way, we can update this adjacency matrix. And yeah, after we have done the query on J, so do the query, then update the adjacency matrix, update the ADJ matrix accordingly, depending upon whether the edge was there or not. And after that, we can just again loop from 1 till n. So for this k, will kind of go like 1 till, it doesn't have to go till n, it can just go till I, or even if you loop till n, then also it's fine. And whichever element that is like adjacent to this j, right? So something like if adjacency of I j comma k, right? So if j and k are adjacent to each other, then you can just flip k, right? So then flip k, something like this. So yeah, so we can do that as well. That if they are adjacent, then we can flip them. And yeah, so this way you will end up with the entire adjacency matrix. So just print the exclamation mark, and after that print the matrix that you already have. So yeah, so just make sure that you kind of keep the color for all the vertices from in the range 1 till I, and you also keep the I cross I adjacency matrix. So yeah, if you keep these two things, then this should be easy. So yeah, so thank you for watching, and I'll see you next time.